loud enough, please.
Okay, so then let us start. So our second speaker in the afternoon session is Deliang Zhong from Tel Aviv University, and he will tell us about line operators in Chern-Simons-Matter theories and bosonization in 3 dimensions. So Deliang, please.
Okay, so to begin, I would like to say it's a great honor to have the chance to speak here, and I do hope maybe in the near future I could come to visit APCTP in person because it's pretty close to China. And today I'm going to report my recent work. Actually last really long with Amit Server, and who is a professor at Tel Aviv University, and Barak, who is currently a PhD student at Harvard. To begin with, just once, wait, sorry. To begin with, let me briefly recall the so-called the Chern-Simons, the self-level rank duality in the pure Chern-Simons theory. For example, let's first ask the following question: what is the question you can write down for a gauge field for of dimension 1 in 3 dimensions? So if you think carefully enough, you will realize there are only 2 possibilities. One is ADA operator, the other one is A cube. Those are the marginal operator you can write down for the Lagrangian. And now if I impose gauging ranks, this completely fixed the relative coefficient to be 2i over 3. So from this simple argument, you see the only dynamical coupling constant is this coupling constant outside called the level of the action. And because in order for this action, a path integral to be well defined for large gauge transformation, for those gauge transformation doesn't vanish at infinity, we can see that this level or coupling constant is actually an integer. So people have noticed that this theory is topological, and the precise meaning in terms of correlation functions that we consider correlation functions several different loops, and if I deform the shape of say one of the Wilson loops infinitesimally, the value of the correlation function will not change. So that's why it's called topological. More interestingly, this theory possesses a new non-perturbative duality called level rank duality, which consists of 2 parts. For example, for definite, let's take the gauge group to be SUN, and we have the rank n of the gauge group, and the coupling constant k is called level, and it has shown for a gauge theory of SUN and level k, if I compute the correlation function some observables, which is equal to the a correlation function same observables, but in a different theory, whose gauge group is SUK, and gauge group is SUK and level is n. So this is a non-trivial duality. Once we couple Chern-Simons theory to matter fields, to mimic the reality, it is known that those matter fields will break the topological nature. So the Chern-Simons-Matter theory is no longer topological. But for instance, if I couple to the theory to a fundamental matter field, and one can see, for example, in the large n limit, this symmetry, topological symmetry, or the reason for topological symmetry is because there possess some high spin symmetry. But those high spin symmetry, although are broken but slightly broken, means they are suppressed by 1 over n. And the duality, this level rank duality I explained about, is expected to extend the duality between bosons and fermions. Those are all in the fundamental representation of the gauge group SUN. And this duality is believed to be held for any, for finite n and finite k, but most of the evidences come from the large n. They consist, for example, people compare the correlation function of local conserved charges in both fermionic theory and bosonic theory, and And then they consider some very heavy operator like monopole baryons, which allows them to determine the some very detailed version, like whether the group is SU or U. Then people also consider some very common observables like thermal free energies or the scattering matrices. Finally, to leading order, they also find those the duality of correlation functions. They can relate those to the well-established supersymmetric duality. Since this subject has been initiated roughly at the same time as APCTP, so there are, I would say, thousands of papers on this subject. So it's a bit hard to give references in my talk. So I list some of the names below. And for the rest of the talk, I will not give any references. But if you really want references, you can take a look of our paper where all the references are properly cited. Okay. Let us first motivate why do we have such duality. For example, we have to first go back to the pure Chern-Simons theory. For example, if I consider expectation value of the Wilson loop, just a circular Wilson loop, it is known, although there's no coincidence, the coincidence limit when two gluon propagator collide, it's a finite number. But if we just do things naively this way, the theory will lose its topological nature. And the way to fix this is to introduce a regulator called framing vector. It's essentially an infinitesimal normal vector to each point of the loop. And it serves, in our physical language, it's just a point splitting regulator when essentially we have gluon propagator along the two loops, along the loop, and I do a point splitting when they collide. And then I take the limit where this length of the framing goes to 0. And people have found the way the Wilson loop defined with this regulator is topological. But however, the price to pay is that even when the framing vector, the length of the framing vector goes to 0 limit, the expectation value of the Wilson loop remembers some details of how the framing vector goes around the line. And for example, shown here, the expectation value is proportional to some fixed number times e to the I pi lambda times some integer. This integer called self-linking number counts how many times the framing vector winds around the original curve. And in today's talk, I only focus on the planar limits, like the rank of gauge group goes to infinity, and the 12th coupling defined as the rank over the level, which is a fixed number. With this framing vector, we can give a very intuitive, classical explanation. Sorry, I shouldn't say classical, but a semi-classical picture of why when I couple a Wilson line to a fundamental source, its spin will change. For example, let's consider some fundamental sources and attach a semi-infinite Wilson line. Because of the framing vector, it is proper to think not to take it as a line, but think this as some kind of ribbon with some thickness, where the second edge of the ribbon is determined by the framing vector. And what interestingly, so for example, I do a 2-pi rotation around this ribbon axis, for example, locally this. And if I do a 2-pi rotation, my fundamental source goes back to itself, but this ribbon will get twisted by one more times. And as we shown here, if I twist the ribbon by one time, the price to pay is I got a new additional phase factor, e to the I pi lambda. So if I look at here, originally under 2-pi rotation, my source got phase e to the 2-pi is, but now it becomes 2-pi is plus I pi lambda coming from the Fermi. So it means the particle gets a fractional spin equals to lambda over 2. Of course, this is just a classical picture because I assume there's no interaction between the matter fields and the gauge field. And so today we are going to consider the same thing, but in a dynamic way. Like for example, I consider there are two different versions of the duality. Involves involves coupling the Chern-Simons theory to either fundamental boson in a minimal way like this, or coupled to fundamental fermion, just usually a minimal coupling. But the point is both bosonic theory and fermionic theory has two, if you want, two conformal fixed points. For example, one in the UV, one in the IR. And both UV, those two fixed points are related by some double trace RG flow. So in the following, when I say both bosonic theory or fermionic theory, I mean the bosonic theory at a conformal fixed point. For today's talk, it's irrelevant which fixed point I'm talking about. So because as we will see, the expectation value, the observable I'm considering is insensitive to the details of this UV or IR fixed point. Although there are many studies on this subject, but in our work we find there's no very natural but yet unexplored observables. That's what we call mesonic line operator. This is a non-local operator obtained by putting fundamental field and anti-fundamental field on two different space-time points. So in order to maintain gauge invariance, we have to connect it by a Wilson line. So that's what we. So of course, this is literally, if it's in QCD, it's a meson. So that's why we call it mesonic line operator. So what we have done is we first classify what is the conformal line operators that can stretch between these two fundamentals. Then we classify all possible fundamental and anti-fundamental operators that can end on these lines. Those two cases are done when this line in the middle was straight. Then we can study what happens when this line is non-straight. This is done by studying the so-called evolution equation or loop equation, if you are more familiar with. The basic idea is Taylor expand the new path around some reference paths, and you will see the price to pay is what I got is insertion of some new operator and integrated on the reference path. So this new integrating is called displacement operator. And I'll show you in our theory, in the planar limit, this displacement operator has some nice properties. Finally, it's by studying those, we got two interesting results. First is a line bootstrap program. We see that we can actually make use of evolution equation to fix the expectation value of the mesonic line operators, which is confirmed by perturbation theory for the first fuse. And second thing is the duality. We can show the line operators in fermionic theory or bosonic theory. They have satisfy the same evolution equation, and they have same spectrum of the fundamental and anti-fundamentals can end on the line. So in spirit, this is where I like to say, when I proved line operating in bosonic theory is equal to the line operating in the fermionic theory, I show them they satisfy the same differential equation, and they have the same initial condition. Then by the uniqueness of the solutions, so they are the same. So that's one way to think about the duality. And this duality is actually a non-productive duality. For example, remember we have two. Let's forget about what is the detail. So the take-home message is the fermionic coupling is related by bosonic coupling minus the sign of the level of the bosonic coupling. So we see lambda goes range from -1 to 1. And when lambda is 0, it's weakly coupled. And when lambda is non-zero, it's strongly coupled. So we see when lambda, for example, say KB is positive and the lambda B is 0. So lambda F equals to -1. So a free boson is dual to a strongly coupled fermion. And on the contrary, if lambda B is 1, when the bosonic theory is strongly coupled, lambda B -1 is 0. So it's dual to a free fermion. Qualitatively, we also compare the two-point functional displacement operator. For example, we have the line and we insert two displacement operator on the position xs and xt, and we divide by the expression value by the same line operator without the insertion. By conformal symmetry, we see there are some conformal function, and what is non-trivial is the function lambda. And this function lambda turns out to depend on the dimension of this boundary operator, and is given by the following expression. And the appearance of this sign is quite surprising, but it's very crucial for the duality. And the relation of delta to lambda depends on theory, but I have to emphasize for both parts of the duality, the dimension, the physical quantity are the same, like spin and dimension are the same. But what is the relation between the dimension and the coupling constant depend on the theory. Now I can, before I go to next section, I assume like the bosonic level is positive. So it means the bosonic coupling goes from 0 to 1, and fermionic coupling is negative and it goes from -1 to 0. The other sign related to this by parity. So parity is okay. The first part would be the duality. Recall. So let's go step by step. The first step is to study the bosonic line operators. Recall I said in the bulk from the three-dimensional perspective, and I sliced into the three-dimensional conformal fixed point. However, this is not enough to say that all operators are conformal, because for non-local operators, those operators can still have the RG flow. And in particular here, I'm considering a Wilson line in a three-dimensional conformal field theory. It still have the RG flow. For example, this can be confirmed by a two computation of the expectation value of the Wilson line. And what we find is, in order to have the conformal line operator, we have to turn on a biscalar adjoint operator on the line. Dimension-wise, this is not very surprising because any marginal operator we can put on the line must have dimension 1 as for the gauge field. But you know, in 3 dimensions, scalar has dimension 1/2. So 2 scalar has dimension 1. And in order to make an adjoint field, better to have phi-phi dagger. So what is interesting is we managed to compute the beta function and find at conformal fixed point, this coefficient alpha is either 1 or -1. So that's the conformal operator. If you want some analogy, this is very similar to 4-dimensional super Yang-Mills cases where we know the Wilson line is not Wilson line has an RG flow, and a true conformal line is the kind of Mendelssohn Wilson line. Here is the 3-dimensional analog of that. We also analyze the RG stability of these two lines, and we find one of them stable or the other one is unstable, but I will explain the details later. After classifying what is a conformal operator, I can now study what are the fundamental and anti-fundamental operator that the open line can end on. So let's Sorry. So let's for that, let's call the fundamental operator a right operator, and the anti-fundamental operator left operator. And I take the alpha equal to 1 line stretching between them. So those are fundamental and non-fundamental only have one indices, so they can end on the boundary. But similarly, we can put but we can also put some operators on the line. Those are adjoint operators. But I started with a serial which only has fundamental fields. So in order to make adjoint operators, I have to take a product of two one fundamental and one anti-fundamental operators. You can add many, you can times more singlets, but in the planar limit, it just factor out. That doesn't change the final result. So now comes to the question: what are the quantum mechanical what are those boundary operators? For example, let's take the line to be straight and infinite. You see, this straight line breaks a three-dimensional conformal symmetry to its subgroup, like the SL2R, which is a one-dimensional conformal group, and the U1. U1 is isomorphic SO2, which is a rotation around the transverse plane of this straight line. From this symmetry analysis, so we know without computation, we know there are two quantum numbers classifying those boundary operators when they end on the line. One of them is scaling dimension delta. The second one is transverse spin S, which is this U1 quantum number. And the strategy is to let's first start at tree level. So when there's no interaction, for example, I don't see this line, and I choose light cone coordinates, like we recall I parameterize the line along the third direction, and I choose a light cone coordinates in the transverse plane. So a complete set of operators is, for example, you can have phi, you can have phi dagger, and you can take light cone derivative to the plus direction, minus direction, or you can take derivative to the third direction. For example, if I take derivative to the third direction, of course, I got the descendant of the fields I had. But this will not change the transverse spin. However, if I take plus or minus light cone derivative, I will change. Of course, I also get a descendant operator, but the spin will change by a one or plus one or minus one accordingly, depending on which derivative you take. However, the observation at tree level is because equation motion is for scalar fields is plus minus is proportional to D3 square. So any mixed derivative can be converted to the X3 derivative. So a complete basis can be obtained by disallowing any mixed derivative terms. For example, like written here, like we defined Ion S, where this N is the number of X3 derivative and the S labels the spin. For example, S is positive, it means I take positive numbers of plus derivatives. And S is negative, it means I take the absolute value of S numbers of minus derivative. I have to emphasize it. I use a physical label. This S is a spin. So if S is negative, it means I take the minus S minus derivatives. And of course, the dimension is related by tree level dimension 1/2 plus the total number of X3 derivative plus the absolute value of the light cone derivatives. So if I turn on interaction, of course, I got a complete set of operators at tree level. So if I turn on the coupling, the total number cannot jump because it's a smooth function. They must be a smooth function with the coupling. So the operator I classified above are still a complete set of operators. But the price to pay is the ordinary derivative becomes a Courant derivative. And in addition, some operators, not all operators are independent. For example, you can imagine you have some operator, for example, OL0S, and you slightly deform your contour in the plus direction, and do a Taylor expansion to leading order. So I expect that's because you're roughly speaking, intuitively it's like your infinitesimal. I do an infinitesimal Wilson line in the plus direction. I'm just saying infinitesimal Wilson line in the plus direction is like the plus Courant derivative, or Courant derivative in the plus direction. So operators can be related by those ways, have the same enormous dimension. So after those classification, we find there are 4 operators, for example, OL00. Let me recall OL00 is just left operator is anti-fundamental, so it's just phi dagger. And the OL0 minus 1. We recall minus 1 is has a spin, minus 1 is a spin, so it's a D minus phi dagger. And similarly for here, it's phi and D plus phi. The crucial observation is these 2 different towers has opposite enormous dimension. So we don't expect any such Taylor expansion relation between them. So that's a conclusion, and now I can briefly explain how we did it. The strategy is to take a specific gauge, light cone gauge, and resum perturbation theory. First, we can resum perturbation theory to find exact enormous dimensions for all the operators. They are equal to lambda plus or minus lambda over 2. Similarly, we can also resum the Feynman diagram contribute to the spin, and you will find it still equal to. We can, like, the transverse spin and the enormous dimension can all be found by perturbation theory, and they can be summarized as follows, like 1/2 plus n plus absolute value of s. You see, it's very similar to the tree level result. The only difference is that the tree level spin is replaced by the quantum corrected transverse spin. And of course, let me show you how this transverse spin looks like. For example, the quantum transverse spin looks like the classical part plus lambda over 2. So you can imagine if I have the boson with spin 0, and at the strongly coupled region lambda equals to 1, the full transverse spin goes from 0 to 1/2. So it becomes a fermion. So that confirms our intuition in the very beginning. Like I attach a line, and the self-interaction line gives the fractional spin of the particles. The final question we can ask is the stability of the operator under RG flow. And this can be done by finding, this question is essentially asked like one-dimensional. We ask what is a small adjoint operator with the smallest dimension. So because I have, as I said before, all the adjoint operators are obtained by products of fundamental fields. So we just pick the minimum, pick the two fundamental fields with minimal dimension. Those are just phi and phi dagger. But because of the quantum correction, those 2 phi and phi dagger all obtain a positive anomalous dimension. So this adjoint operator at the conformal fixed point has a dimension bigger than 1. So if I turn on it, it's irrelevant on the line. So that's why this alpha equal to 1 line operator is stable under RG flow, and it's a stable fixed point. After this, we can ask what happens for non-straight line. That's like the evolution equation. First, because we know we have conformal symmetry, so we have conformal symmetry, and we know the boundary operator has some spin and have some weight under conformal symmetry. We can first factor out the spin part and the weight part. What remains is f. F is if we want conformal invariant functional of the past that's the only place where the path dependence enters. And now we can study this so-called loop equation, like extending the Wilson line amounts to linear order, amounts to insert this so-called displacement operator on the line, and I integrate it along the reference line. What we find in this, surprisingly, in this theory, we find the displacement operator in our case is a chiral operator. It has exact dimension 2 and spin 1. Or for example, I listed 2 components of the displacement operator. You see it's made of phi and d minus phi dagger. You see for what is non-trivial is the following. This operator must have exact dimension 2 and spin 1, so the integration makes sense. Otherwise, it doesn't make sense. So you see what happens here is it is made of 2 fundamental fields with opposite anomalous dimension and opposite anomalous spin. And because to linear order, the Lagrange factorization, the dimension of D is just the sum of the dimension and spin, just the sum of the 2 fundamental fields. So the anomalous dimension and anomalous spin cancel between them. So we got a displacement operator with dimension 2 and spin 1. So which is exact, I have to emphasize this exact, quantum mechanics is still 1. The final missing ingredient is the so-called boundary equation, which is nothing but a generalization of this equation motion at tree level. For example, what is non? For example, you can consider this d minus acting on. Essentially, let me put it different. Let's consider this equation d minus d plus d minus. I think as the 2 functional derivative acting on the some operator, and I can first act on this minus derivative to some operator, which gives some spin. For example, here it has some minus spin because I add minus derivative. However, quantum mechanically, we know this operator has some anomalous dimension, anomalous spin. So when I take one more plus derivative, there's only one candidate in the full list of the operators that has the same spin and whose twist is reduced by 2, and that operator is the descendant of OL2 minus S. So without doing any computation, we know there must be the only relation between this left-hand side is this only operator, and what we need to find is the coefficient beta. So different operators with different anomalous dimension cannot mix because they don't have because the spin and dimension are different. Put it differently, what I'm just saying, at tree level plus minus, there's no difference between the plus minus and minus plus. But quantum level, when I first plus and the minus has different anomalous dimensions. So once you take one derivative, the other derivative cannot take it back to the same tower. So, and we managed to compute these 2 coefficients, one by perturbation theory, also by the bootstrap method. I will explain in a while. That value, the beta and beta bar is still 1/2, so they remains to be the tree level value. After finishing the bosonic part, we can ask what is Permianic dual operators. So I can repeat exactly the same thing. Like I have alpha equal to 1 line in the middle. I have fundamental and anti-fundamental fields. What makes story simpler is because to linear order in 1 over n, I have some adjoint boson pair on the line, but they don't couple to the fermion, boundary fermions. So I could say naive Wilson line is a conformal operator in this case. but the meaning is to linear order in one order is conformal. And we can also classify boundary operators, like the fundamental operator. We can have the fermion. We can take three light cone derivatives. We can take three derivatives. Here I label the fermion by its transfer spin. So psi plus has a transfer spin 1/2. Then I can take many derivatives, as I said before. And still, I don't allow any mixed derivatives, because they can be reduced to D3 square by equation motion. And what we find is, in both cases, we are able to match the spectrum and the evolution equation for the fermionic operator and bosonic operator. And in particular, the first few operator, let's focus on the first one. For example, the right operator, the normal boson, psi got a phi, got a minus anomalous dimension and the positive anomalous, minus anomalous spin and positive anomalous dimension. And this matches with the fermionic operator of psi. Here I write the spin and the dimension in terms of the bosonic coupling. So what we did is we compute the psi and using the fermionic couplings, and then we compare these two using a dictionary I described above. So now we find a perfect match. We see some component of fermion is matched to the scalar, but the other component is matched to the derivative of the scalar at tree level. So this map is slightly non-trivial than we thought.
Is it perturbative, this result, or it's all order? Or?
So sorry,
Is the result perturbative?
All order, exactly in one or n, but it's all loop computation. It looks like it's one loop, but this is a line operator, so it's not exponential or something. To put it differently, the leading order tree level is 1, and one loop is log of the cutoff, lambda times log of the cutoff. Second order is lambda square times the cutoff square over 2. And after resum, you get the anomalous dimension is lambda b over 2.
Okay.
So we can repeat the same thing for the alpha equals -1 line, but we can skip the details because I think I'm almost running out of time. But the physical picture is to linear order in 1 or n, the anomalous spin is completely due to the gluon self-interactions. So you recall this sign of alpha is just the sign of the biscalar coupling, which biscalar doesn't have spin at all, so cannot give the fractional spin. So the expectation is regardless of sign of alpha, the anomalous spin is still the same. But relation between the anomalous spin and the dimension will change, and indeed this is confirmed. And the chirality of this displacement operator is kind of flipped. Yes, is someone asking? Or? Oh, no. Surprisingly, we find the dual fermionic operator is more complicated. For example, the first hint comes from the fact that when bosonic coupling goes to when I have a strongly coupled boson, which is dual to a free fermion, I have this phi and phi dagger and phi, both dual to both have dimension 0 and spin plus minus 1/2. So I must find some fermionic operator in the free series has dimension 0 and spin 1/2. But spin 1/2 is quite not surprising because fermion has tree level spin 1/2. But in order to have dimension 0, we know tree level fermion has dimension 1, so we have to integrate them along the line. So after some thought, we find the answer is the alpha equal to -1 mesonic line or mesonic line operating in the bosonic series is dual to the following so-called condensed Permianic series. It is obtained by inserting a pair of fermions integrated along, where these two endpoints are all integrated along the line. And we for the empty part, we have to recall I have the, when I say this has the spin, I mean the spin at the endpoint. But if I just integrate the fermion in the middle of the line, the spin transfer spin is at the bulk point. So I have to introduce some function to parallel transport the fermion spin from the bulk to the boundary to the endpoint. And this was done by introducing a new function called string transport gamma. And it's okay. I don't have time to explain this gamma function. Sorry, how much time do I have? Should I finish soon or?
How much do you need? You can wrap up like in 5 minutes, 5 to 10.
Okay, enough. Thank you. Let me wrap up in 5 minutes. So this operator is very similar to the, if you are familiar with ABGM theory, this is the Permianic operator found by this Drucker and his collaborators. And similarly, we repeat the duality computation. We find the same spectrum, same evolution equation. Like we are able to match the boundary operators. And so this gives us a hint that those theories are dual to each other. But surprisingly, this operator we find is not stable under RG flow because we repeat the same story, but here the adjoint operator phi dagger has a negative anomalous dimension, so it's becomes relevant. So when I add this conformal point, I turn on this relevant perturbation, and I will leave this point. So I will either go to the alpha equal to 1 fixed point, or I go to the alpha equal to infinity fixed point. So so if I have, as I said, I have 3 more minutes. Let me briefly wrap up the bootstrap session. First, by far, you see, I do everything in perturbation theory. I didn't use the evolution equation at all. I use it, I use it to prove they are the same, but I didn't try to solve it. And the first question is, can we solve the evolution equation? And at the formal level, the answer is yes. That's what we call perturbative bootstrap. Like once we can make an ansatz for the one loop mesonic operator as some line integration, some function, and by using those equations, we can determine those functions. So in spirit, this will really like this original 4-dimensional QCD loop equation. Like the advantage is, of course, we don't need to do any gauge fixing. I don't need to draw a Feynman diagram. Those equations are strong, but the drawback is the solution we obtain this way are quite formal because, as you've seen before, the divergences are come from the endpoints. So if I don't do any line integrations, I cannot see those. So that's why it's a very formal thing, but still. It's kind of the analogy of the 4-dimensional QCD loop equation can be done. Now we come back to the more interesting part is the physical bootstrap. Namely, we find that by using the perturbative spectrum boundary operators and using the equation evolution equation, we can determine the expectation values of those mesonic line operator. For example, recall. Have some spin and weight. I can when it's a straight line, this conformal invariant function of the path become a number, and we are able, those evolution equations are enough to determine those numbers. So the basic idea is to take the evolution equation, and I think, and just act on it on this operator. Namely, I assume the evolution equation applies to the operator non-perturbative with even at finite coupling is correct, and I demand conformal symmetry order by order to fix the coefficient of all possible. It then becomes a conformal perturbation theory, where the expansion parameter is now becomes a deformation, numbers of deformation, orders or order of deformation. For example, at second order, those are the typical relevant marginal operator on the line. Then I demand this operator is like a translation rotation invariant. I can fix the coefficient, and after doing that, I can fix the value of f. So the final result gives us the displacement operator 2-point function, and this function lambda is not. You see, it has many important physical meanings because it's also the 2-point function of displacement operator on the circular Wilson loop. Let me conclude by give some outlooks. So we can, next step, natural step is to consider a connected 2-point function of such mesonic operators, and we believe we believe the connected part. Once we have this, we essentially showed the leading to kind of give the proof. It would serve as a proof for the duality to leading order, and we expect some the spectrum what we find already plus the spectrum local operator are enough to determine this. And we also want to solve the path dependency implicitly, like I know the one loop answer, but higher loop is not known. Also, the original motivation is to derive the holographic dual, but yeah. Okay, I'm over time, so let me. Thank you very much.
Thank you, Deliang.
Yes.
Okay, so are there any questions? Are there questions from the online audience? Okay, doesn't seem to be the case.
Okay.
So yeah, maybe this is like a perpendicular direction of integrability. But so let me ask a question.
Okay.
I guess you can use this approach to consider supersymmetric version of this Chern-Simons theory, which is AVJM. And have you done anything in that case?
Not yet, but I agree. This can be. If you want APCTP is, I can consider kind of two bifundamental fields and two Wilson lines, one kind of one in one gauge group, one in the other gauge group. That would be the generalization.
Do you expect it to be like straightforward, and can integrability be of any help in this case if you take like planar limit?
I think so. I hope is with if someone studied this operator I described, we would able if we could find some integrability description of this operator.
Yeah, because in that case it might really help with the holography, right? Because we already know, at least in the planar limits for AVJM theory, it is
yes.
type 2A.
Yes.
I see.
Yeah, we can draw some hints from both holography and integrability. If we find some this kind of algebraic equation determine the expectation value, it would be nice. So. Because here I do everything in brute force perturbation theory, I don't expect I can do it in AVJM. Yeah.
Maybe yes. Yes.
Yeah.
But anyway, the final result seems to be simple, at least.
Yes, I think put it different. This operator I'm considering can be seen as kind of ABJ theory with one of the gauge groups, the rank goes to 0. Okay, so
Uh-huh.
and one
Right.
gauge group is trivial, so there's no real bifundamental.
I see. Okay, thanks. So if there are no further questions, let's thank Deliang again